Okay, well, in the last video on this Mobius inversion chapter, and so we've led up to the Mobius inversion formula by first taking a look at what is the Mobius function, proving that it's multiplicative, and then showing that it has this really interesting role in reversing, or I guess inverting, relations between summations of number theoretic functions, and that's the theorem that's in front of us here. So let's take a look at sort of the implications. You should think of the Mobius theorem or the Mobius inversion formula theorem as something that's really broad. I mean, you notice that we didn't say anything about what big F or little f, well, I guess what little f is here. This can be any number theoretic function, be it tau or sigma or any other one we care to define. Um, and it doesn't depend, I don't know if you saw this, but it doesn't depend on f itself being multiplicative. Um, so it's a very broad and general theorem, which makes use of the Mobius function. Okay, well, let's take a look and see what, recall that, I mean, what the implications of the Mobius inversion formula are on some, I guess, functions that we already have been introduced to. So let's take a look at tau first. Remember that tau counts the number of divisors that a natural number has. So if we recall the summation notation for tau, tau of n is just the sum across all divisors of n of 1. So all it's doing is counting how many divisors exist. And the question is, what's the implications for Mobius? Implications on this function for Mobius inversion. So let's take a look at what the implications are here. All right. So let's just think about this first of all. So tau of n is equal to the sum across all divisors of n of just the number 1, right? So the way I sort of think of this is I think of this as, well, this is your big F of n here, right? And here is your little f of, I don't know, we'll call it d, right? And so I guess, we can kind of think of big F of n is just equal to tau of n. And so I'm sort of putting these in quotes, right? And little f of n is just equal to 1, right? That's the function that we're summing across. And so what does Mobius inversion say? It says that, I'll just sort of put this over here, right? And say, well, this says that Mobius, I'm going to write it out here really quick, that this is f of n, again in quotes, I guess. So this is the formula, is equal to the summation of all divisors n mu. I'm going to use the n over d formula. Oops, f of n, or big F of n, sorry. And it's big F of d, sorry. There we go. So this is what the Mobius inversion says to do. So big F goes right there. So now in this particular case, what is f of n? Well, f of n is just 1, and so that means that 1 is equal to the summation of every divisor, across every divisor of n, mu of n over d. And big F of d is, well, that's just really tau of d, right? Evaluated at d. So this is the implications of Mobius inversion, right? On tau of n. What it says is that if we I guess, sum across the value of the Mobius function times the number of factors of each of the divisors of n, that sum will always be equal to 1, which seems kind of hard to believe, right? So let's just see what the example gives us here. The example I have worked up is n equal to 15, which is just 3 to the first times 5 to the first, right? And supposedly, we're going to take a look at the summation of every divisor of across every divisor of 15, mu of 15 divided by that divisor times tau of that divisor. So what do we get here? I guess there are 4 divisors for 15, right? So let's just go through them one divisor at a time. So mu of 15 over 1 times tau of 1 plus mu of 15 over 3 times tau of 3 plus, I wish I had more space here, I'll just put it down here, mu of 15 over 5 times tau of 5 plus mu of 15 over 15 times tau of 15. I'm sorry, this is really messy. I'll put it on this line next. So let's see, let's just write it out without fractions. So we get mu of 15 times tau of 1 plus mu of 5 times tau of 3 plus mu of 3 times tau of 5 plus mu of 1 times tau of 15. So once again, this is sort of, we're seeing this just as factor pairs. That's because of the definition here. So let's see, mu of 15 times tau of 1. So mu of 15 is how many, is what I guess, the Mobius mu function evaluated for 15 is, and that's 1 because there's 2 unique prime divisors, each raised to the power of 1, and tau of 1 is just 1, so we have 1 times 1 here. Mu of 5, that's going to be negative 1, and tau of 3 counts the number of divisors of 3, which is 2. Mu of 3 is also going to be a negative 1 times tau of 5, the number of divisors there, of course, is 2. And then mu of 1, which is defined to be 1, times tau of 15, which is the number of divisors of 15, which is 4. And so what do we get here? We get 1 minus 2 minus 2 plus 4, and indeed that's just 1. So it appears that we've sort of come to it. I mean, it's almost like a new theorem, if you want to think of it that way, that tells you something about sums of divisors. I guess the number of divisors, the number of factors of a number's divisors add together to make a sum of 1 if we attach the Mobius mu function in front of each of them for its factor pair. Boy. So in other words, the implications are Mobius inversion on tau of n gives you a completely new relationship you would have never probably ever realized was there. And it's all tied to sort of the coefficient that comes in front, I guess, of the big summation function being attached in front of it. So kind of a neat implication. You get sort of a new result using Mobius inversion on tau. Well, as you might expect, I mean, if we take a look at Mobius inversion on tau, we should probably take a look at Mobius inversion on sigma, and recall that sigma also has a summation notation, which allows us to think of it like a big F. So what are the implications here? Let's take a look and see what's going on with this one. So again, we start out at the top, sigma of n. We think of it as a summation of all across all divisors of n of the value of the divisor. This is the sum of all divisors, right? So we can kind of think of this guy as our big F of n, right? And it really means, I guess, what I think of it is F of d is it's tau of d, right? And we can think of this like our little f of n, and here it would be, I guess, f of d is equal to d, right? It's the identity function. Okay, so we know that the way Mobius works is these two guys get flip-flopped in Mobius, and I mean Mobius says that what you get here is f of n is equal to the summation across all divisors of n of mu of n over d f of d. That's what Mobius says. It's sort of the generic version. But we have now identities for these functions, so let's put in what we know. So this thing is equal to f of n, and f of n is the same thing as f of d equals to d, right? So in this case, if it's f of n, we'll keep the n notation. This would just be n is equal to the summation for every across the divisors of n of the Mobius function evaluated at n over d times, oh, sorry, this is big F here. I messed that up. So big F of d is just tau of d. So again, we get kind of a new, this is Mobius on sigma of n. Gives us this new, I guess this is the implications, right? Of Mobius on sigma of n. And what it tells us is that if we sum across the divisors of a number, the sum of each of those divisors, and then multiply those by the Mobius value for the, I guess, the numbers factor pair, then that whole sum should equal the number itself. So let's just check this again for n equal to 10, which is 2 times 5, right? So we're looking at this idea of all the divisors of 10, evaluate the Mobius value of 10 divided by that divisor, multiply it by the sigma value of that divisor, and what we want to check is to see if that's actually equal to 10 here. So I'll just say this is equal here. I have a little more room. So let's see, it would be mu of 10 sigma of 1 plus mu of, I don't know, sorry, not mu, sigma here, mu of 5, let's do them in reverse order, 5 times sigma of 2 plus mu of 2 times sigma of 5 plus mu of 1 times sigma of 10. Let's see, mu of 10, that's 2 times 5, so it's going to be 1 times sigma of 1, which is 1. Mu of 5 is going to be negative 1 times sigma of 2, which is 2 factors for 2. Mu of 2, that's going to be a negative 1 times sigma of 5, which is 2. Plus mu of 1, which is equal to 1 times sigma. Oh, sorry, I'm not adding them, or am I? Sorry, this one is not 2, it's 3, because sigma is the sum. I was using tau here. And this one is not 5, it's 5 plus 1, or 6. There we go. And then this one is going to be 1 plus 2 plus 5 plus 10. 15, 16, 17, 18 is our value here. So let's see what we get. We get 1 minus 3 minus 6 plus 18. You can see that's 19 minus 9, or 10. And indeed, it seems like it does work. Mobius inversion tells us that, if we sum across this particular setting, then we get the number itself. So again, it's almost like a whole new theorem about sigma, the sum, which actually tells you a little bit about how it behaves for the divisors of the number. Um, there's this kind of unique way they sum to be the number themselves, provided you attach the Mobius, I guess, value in front of each, which is either a positive or negative one. Interesting. So let's take a look at just one more example here. I think I have one more that's kind of a fun historical example. Oh, this is kind of fun. If you know that f is a multiplicative function and f is defined in the way that we think of it, then positive f is also multiplicative. So we know that mu is multiplicative, right? So that means that that big f of mu will be multiplicative, right? And so what that really means is that when we invert this, you're going to solve for some f of d, and that particular function will be multiplicative as well. So I guess what that means is that this works in reverse, right? So if Mobius inversion allows you to invert something, if big F is multiplicative, then little f will be multiplicative. Hope that makes sense. Yeah, so here is a number theoretic function that's kind of interesting. This is the Mertens conjecture. It has to do with this number theoretic function. Big M of n is the sum from k equal 1 to n of all of the Mobius mu function values. So maybe we should just take a look at a few examples here. I need to turn on my overhead. Make it bigger here. So if we're thinking of the Mertens function, this is m of n, the sum from k equal 1 to, let's say, n itself of mu of k. Let's just take a look at m of 1. Well, that will be just the sum from 1 to 1. That'll be just mu of 1, which is just 1. This will be m of 2, which will be, I guess, mu of 1 plus mu of 2, which would be 1 plus a negative 1, or 0. M of 3 is going to be mu of 1 plus mu of 2 plus mu of 3. Well, we know it's 0 plus mu of 3, which will be just negative 1, right? So negative 1. Let's take a look at m of 4. That'd be mu of 1 plus all the way up to mu of 4. Well, it's going to be the negative 1 plus mu of 4. And mu of 4, since that's a squared, is not a square-free number, to be 0, so that'd be negative 1. M of 5, well, let's see, that'll be mu of mu of 1 plus all the way up to mu of 5. So we know that mu of 1 through 4 is negative 1, and then mu of 5, since it is a square-freed number and only has one factor, will be a negative 1, so this will be negative 2. To give you a sense, if we kept going at this, m of 10 would be a negative 1, m of 15 would be a negative 1, m of 20 is going to be a negative 3. And it sounds like these things sort of bounce around. That there's sort of this idea like when you get a positive and negative, they start to cancel each other out. But then this thing never grows. It doesn't seem like it's growing very very high. And one way to think of it is this is this is sort of the difference. This number is a difference between the number of positive integers that are less than n, that are of, that are square free, that are either of even length or odd length. So it's the difference between the square free integers of odd length versus the square free integers of even length, I guess. So at 20, what we're seeing is that there are 3 more integers of odd length than of even length. And you would imagine that it's not always negative, that eventually this thing will grow a little bit higher, positive. So let's just take a quick Google search to give you a sense of what this thing looks like for large values. If you type in Merton's function into any, I guess, search engine, you'll see something like this. Give you a sense of Merton's function out to the hundredth, out to 100 integers, I guess, right here. And here we can see Merton's function value out to about 1,000. But you can see that you have large shifting above and below the x-axis, meaning that there are more even or odd square-free integers in that region. But eventually things seem to sort of climb back. I think this is an interesting graph, and makes you wonder a little bit about the construction of numbers and the distribution of square-free integers, and I guess the ones that are even or odd in terms of length. So kind of an interesting, I guess, function in itself. But here's the backstory to the Merton's conjecture. In 1897, Franz Merton published a paper with a 50-page table of M of n for the numbers 1 through 10,000. And on the basis of this evidence, he conjectured that for any n greater than 1, that the value of the Merton's function, evaluated at n, absolute value, so it will always be strictly less than the square root of that number. So in other words, there's an upper bound on how wide this particular curve can get, and that upper bound, both above and below, I don't know if you can kind of see it here, appears to be something like the square root function. So in other words, these peaks can't grow any higher or lower than the square root of the value of n. And it was believed to be true for quite some time. Here's a picture of Merton's conjecture, and you can sure see there's plenty of room for error. Merton had actually calculated all of these blue values, and I included in the picture the actual graph of the square root of n, positive and negative, to account for the absolute value. And turned out it took till 1985 that Andrew Odelesko and Herman to really conditionally prove the Merton's conjecture false. It was later shown that the first counterexample appears below 3.21 times 10 to the 64th, so the first time it actually grows outside of the bounds of the square root curve. But it's so it's below that number, but above 10 to the 14th. So we really haven't been able to find a particular number, or weren't able to find a particular number at first. And no counterexample was explicitly known. And it was in 1979 that Cohen and Dress found the largest known value of Merton's number, which is currently around 50,000. In 2011, Kurtzoff found the largest known negative value of Merton's, which is this number. And in 2016, Hurst computed M of n for every n greater than 10 to the 16th, but did not find larger or smaller values. So you can see that this particular number, which has to do with the Mobius mu function, is of an active research interest to lots of pure mathematicians, and I thought it was a nice way to end the chapter. Okay, that's it on the Mobius mu function. I look forward to seeing you when I get back. Good luck on your homework.